focus on doing some, working some problems on what we went over. But I just wanted to summarize real quick, right, what we're doing, and just in case you weren't here, if you missed Tuesday's lecture. So we started talking about ventilation calculations. So we drew this, and why we're doing this? Well, if we have an evolution rate of a toxic component, we may need to determine what ventilation rate we need to have to keep the concentration of that component in a room below the time-weighted average, right, to keep our workers safe. So we talked about the evolution rate here is, and what we actually derived was evaporation from a spill, for example. So you have a pool of liquid that's continuously evaporating, or if you're actually filling a container, then you'll have evaporation as well as a filling term. The first thing we did was just derive this equation for how the concentration in ppm, right? That really was it. It's just a mass balance, right? And then we convert it from sort of a mass per volume to ppm. That's all we did. That's all this equation does. But it's so that you don't have to derive that. You have the concentration in ppm, because most often that's what you have in terms of your time-weighted average that you need to look at. And then, so if we know the evolution rate and the ventilation rate, then we can calculate what the concentration would be, and therefore see if we need to do something else to reduce that concentration further. We haven't talked a whole lot about this K yet. So see, there's a K. It's a ventilation quality constant, and it's obviously not completely arbitrary, but it's an approximation. So, and it's because we are not going to have a well mixed room. So we're basically taking into account the fact that we don't have perfect mixing. So we're going to talk about how we determine that constant today. Well, we started with evaporation rate and said that obviously QM then is proportional to the pressure difference between the saturation pressure of that component and that component's partial pressure in air, right, where it's going. And then, of course, it depends on the area of the pool and a mass transfer coefficient, which you know where this equation comes from now. We just looked at why are we using this. And this equation is only because so we can use the mass transfer coefficient of something we know, a reference compound. We've chosen water because that's given in your book. Okay, and it's given on the same page, but sort of a little hidden, right, on that page. But you need to know where to find that. And a lot of times, at least in the beginning of a spill, right, our evaporation rate is going to be maximum because we don't have a partial pressure of that component in the air already. So that's when our evaporation rate is the highest, and we can calculate it using that. Obviously, as time goes on, the evaporation rate will decrease unless we have a very good ventilation that keeps it, right, that keeps removing that component. Okay, so that was for evaporation. Then we looked at filling operations, and in the book they've defined RF, which is in units of inverse time. It's the rate, it's like the rate to fill one container, where VC is the volume of that container. But what's important here is that RF times VC is the volumetric flow rate. So that's really, most of the time you're actually filling a liquid. So that's the liquid flow rate that you're filling with. But that liquid is going to displace that volume of gas that's already in that container. So we need QM, so that's a mass flow rate. So we just multiply by the density, and the density for an ideal gas under these conditions would be this. That of course assumes now that we are at saturation of that liquid. Right, the gas phase above the liquid is saturated. Yes?
What does RF stand for again?
The RF, that one you said, it's a filling rate. It's basically the inverse time that it takes to fill a container. And obviously you need to know the volume of that container. So I don't know why they decided to do that. A volumetric flow rate is more intuitive to me. So, and sometimes rather than actually giving you RF, the filling rate is given to you as we filled 50 drums in half an hour, or 3 hours, whatever, however long it takes.
So the RF is in terms of per time weight?
It's only per time.
So the VC is
It's the
the volume.
volume. No, VC is only the volume. Okay, important. RF is per unit time. So it's basically, it's 1 over the time it takes to fill one container that's of this volume. So this is volume, this is time, so you get a volumetric flow rate. Okay, I don't know if I agree fully with that definition, but as you know, when last time, I couldn't come up with a better, because QV they're already using for the volume, right, for the ventilation rate. So it was hard to be consistent. So I guess as long as you know that RF times VC is the volumetric flow rate, the filling rate, in other words, in volume per unit time. But we're looking for the mass flow rate, right? So we just multiply by the density of the ideal gas. But we also talked about this assumes that we are at saturated vapor, which may or may not be true, right? So we distinguish between 2 different conditions. Obviously, again, this is approximations, but if you do splash filling, which is this one, your pipe ends above the liquid and basically all your liquid splashes down. That means that you're gonna have liquid splashing everywhere and you're more likely to have a saturated vapor in this space. If you do subsurface filling, or as someone mentioned, if you fill from the bottom, right, then you might fill faster than this vapor space is saturated. So we take that into account by just multiplying by half. So we're saying that it's half the concentration, in other words, than we would have if we do splash filling. Yes?
Like experimental sounds like theoretical thing?
This, I'm pretty sure this is, they've just tested it, right? If we do subsurface filling, we measure the concentration. So you realize, chemical engineers, right? This is not very quantitative, right? So a lot of what we will be looking at is actually where they've tested it. So for example, later on when we're gonna look at explosion damage, for example, we need to know what the pressure is at a certain point. And I'm sure that someone has put pressure sensors along the end, right? They've blown up a certain amount of TNT and looked at what the pressure is at certain distances, and then fitted an equation. So a lot of times that's the best we can do. And I'm sure it might be some theory behind it. In this particular case, I kind of doubt it, I have to say, right? So, but it means you have to take everything with a little grain of salt, right? And know what the approximations go in to your equations, right? And also, I've questioned this one myself, because a lot of filling operations, you're not filling an empty, this assumes that you are filling an empty container, that you're starting with it, because then it wouldn't have any vapor space already. Because if you have any liquid present when you start filling, it's already saturated. Which means, so in other words, if you want to be completely safe, you should probably go with a 1, right? in here, stating assumptions, any assumptions that you have made, right, on the exam, for example, is critical, because that's the only way I can judge whether or not you know what you're doing. Okay, so if you're on an exam, for example, it says subsurface filling, and you use, theta equals 1, that would be taken, I would have points taken off for that. Unless you clearly tell me that, well, I don't know if the container was empty when the filling process started, so to worst case scenario, there might have been liquid left, the vapor space is already saturated, so I'm gonna assume 1, right? As long as you clearly state what assumptions you have made, you'll get more points.
How can it be subsurface filling if the tank didn't have stuff already?
So, very good point. Did everyone hear that? How can you do subsurface filling if you don't have any liquid in it to begin with? So the key there is that the pipe goes all the way down to the bottom. So there's not really enough room for it to spill, and after a few seconds, you're gonna do subsurface filling. So.
So we're trying to get from the pipe to get up, it's going up to the bottom instead of subsurface, and we can fill into an empty tank.
Say that again. So now we're filling from the bottom.
Instead of pipe coming to the top, again to the bottom, would you fill subsurface even in an empty tank?
Yeah, I would say so, because you're certainly not doing splash filling in that case, right? But it's hard to do filling from the bottom, right? Yeah, of course, but which you would have to do anyway. But you have obviously you have to make sure that your valves, because usually you drain it through the bottom and use gravity. So it's another one of those where you have to make sure that the right valves are closed when you're actually filling, because otherwise you might not be filling the tank, you might be filling the rest of the process, right? Yes.
Would phi ever be like a sliding scale between 0.5 and 1 as it rose towards the pipe? Did you ever do that?
So we are not going to handle these are sort of the two extremes. It's either we're dealing with subsurface filling and we use half, or we're dealing with splash filling and it's 1. Obviously, you can be anywhere in between, but we don't really know, right? We can't determine accurately. So at least we can get a range. It's going to be between these. And if you use subsurface filling first, and you're close to the time-weighted average value, right, the concentration that you're calculating from the ventilation calculation, if it's close, then you might go back and be, okay, we have to be more careful here now to make sure that that vapor space here is not saturated. Okay, so for filling, we have an evaporation term and a filling term. So this is just the filling, this is the displacement term, this is evaporation, which could be smaller or not. It depends on the opening that you're filling through, right? So we added those together and got something that looks like the evaporation term with just the filling added to it, and we can add this QM back into our CPPM calculation. And by doing that, now we have PSAT, and then we have the total pressure. We also have the temperature of the ambient temperature and the temperature of the liquid. And this equation assumes that they're equal. Okay, that's why the temperature disappeared. Which in most cases, that's what we're gonna have, right? Because it's a filling operation. So if you have a tank truck coming in with something that you're filling in a tank, they're probably both outside, it's gonna be approximately the same, so it's not too far off to assume that they're equal. Okay, so what we didn't get to last time was to actually look at this and do a problem. So 324, we have 55-gallon drums are being filled with 2-butoxyethanol, and they're splash filled at the rate of 30 drums per hour. Okay, the opening through which we're filling has an area of 8 centimeters squared. And we're asked to determine the vapor concentration, the ambient one, if the ventilation rate is about 3,000 cubic feet per minute. Okay, so 3,000 cubic feet per minute, that's a pretty high ventilation rate. And it's a typical one that's used for outdoor filling. So if we do indoor filling, we actually might have lower ventilation rates than that. In this particular problem, we're given the vapor pressure, and it's 0.6 millimeter mercury. In other cases, you might be given the temperature, and you basically have to calculate the vapor pressure yourself. And we're going to look at how to do that too. There is we have to use the Antoine equation for vapor pressure. So we'll look at that too. If not today, then next time. Okay, so let's see if we can make it through this problem today. I'm gonna leave that up there. I hope that I can fit everything else because we're gonna write. You know that we need this K, right? So this is 3.4. So in that equation, what I normally do is instead of setting up CPPM is equal to QM over K, QV, and all the rest, I move this K over to this side and calculate the rest. Because this K is unfortunately dependent on the CPPM value here. So we can't determine this until we know what range this will be in. So it's easier for us to do this. And then what we have is our saturation pressure, our QV, total pressure, and then we have our filling term and our evaporation term. Okay, so of course we've got gallons, drums per hour.
Do we need a times 10 to the 6?
Say say that again?
Do we need a times 10 to the 6?
Yes, thank you. Otherwise it wouldn't be ppm. Okay, so we have 55 gallons. That's 50 gallons per drum, right? And we're filling 30 drums per hour. And we have a fill opening. Our area in this case, which is area of the hole, right? The drum is 8 centimeter square. So just keep that away from the area of the actual tank if you're given. It's not given in this particular problem, and we are not told. We have to assume that this is, if you're filling through the pipe, if you're looking at it from above, that's the area of the pipe, right? And that's the area of the hole. You're probably walking a little bit. So in this case, we're not given any geometry, so we have to assume that this is our area, right? Okay, what else do we know? So what do we have? We have our RFVC volume per unit time. It's 55 gallons, which is, what do we have? What more do we have? 55 gallons, our VC is 55 gallons, which is equal to 208, 175 cubic decimeters. That's per drum.